Hello, everybody. Maybe we can start. It's 3:02. I would like, on behalf of the Athena Science Study team and the community office, to thank Margherita to be here, our speaker of today. Just to present her, she had a PhD in astronomy at the University of Bologna in 2011 on a thesis on accretion disk winds and active galactic nuclei. Then she had countless postdoctoral experience. Just to mention a few, she was as a research fellow at ISAC in Madrid. Then several years in Estron, where I think I first, actually, when I first met her. And then she came back to Spain at the Centro de Astrobiología in CSIC. And since then, she's in Spain. She now is the principal investigator of an Atracción de Talento, its project, with a co-financed between the Madrid community and the Instituto Nacional de Técnica Aeroespacial, and where she is, and she works on AGNs from many different aspects. So thank you very much for being here, and we're looking forward to your fantastic talk. Okay.
Thank you very much. Thank you very much, Nanda, for inviting me, and thank you to everyone who is attending this presentation. Let me start sharing the PowerPoint.
Yes, go ahead.
So this is the story of a completely unexpected cosmic phenomenon that really left us completely surprised. And actually, the words unexpected, surprising will recur many times during this webinar. I want to thank a lot both Giovanni Minuti, the QPE discoverer, and Riccardo Arcodia, who is doing a great job in keeping up the enthusiasm about this amazing cosmic phenomenon, and of course also many other important collaborators. This is the outline of the talk of today. So the main body of the webinar will be devoted to introduce you to the vast amount of observational data that we got about QPEs. And then I will try to also introduce you to the different physical scenarios which are possibly able to give us an interpretation of these observations. And I will conclude to telling you what we can expect during the next decade, so during the Athena era. So all the details of the observational results about quasi-periodic eruptions can be found in these articles here. And please keep an eye on the archive during these days, because new interesting results are going to appear during the following weeks. So our story begins close to the South Galactic Pole in that direction, but looking back about 250 million light years in a galaxy which was really not famous at all, especially for X-ray astronomers. The name is GSN 069. It's also a two-mass source. And it was really unknown to us because it was not even detected by ROSAT during the all-sky survey performed in the 90s. And then in 2010, when XMM Newton was slewing from a target to another, a large amount of photons were detected coming from that exact direction. So in this plot, you can see the upper limits observed by ROSAT in the 90s, and then the soft X-ray flux observed in 2010 by the XMM Newton. This is a huge difference in X-ray flux of a factor of more than 200. And so immediately XMM Newton pointed again the source, and also monitoring with SWIFT started, which lasted several years. And this decline in X-ray flux is consistent with what is expected from a long-lived tidal disruption event, meaning the difference in flux between what was observed by XMM and what was not observed by ROSAT is consistent with the energy released by a star, which approached the central black hole of the galaxy too much and was either partially or completely disrupted. This is also has also been confirmed very recently by a detailed study of the UV spectrum of the source, where an abnormal carbon over nitrogen abundance is completely consistent with the partial disruption of a red supergiant star. So large X-ray telescopes pointed at this source a few times after the discovery, And I will show you here the light curves of the source as observed by XMM Newton in 2010. So just after the discovery, there was a more or less 10 kiloseconds pointing. And the light curve was not displaying anything really unusual for a galactic nucleus. So random variations of flux up and down, on really with no, nothing really unusual. Then 4 years later, the source was observed again for a much larger amount of time. And again, the light curve was showing nothing exceptional, except for a very constant low flux, which is something pretty unusual for AGN, because usually they display a pretty erratic and very strong variability on these time scales. And then at the end of 2018, XMM Newton was pointed again at the source together with Hubble. And during 45 kiloseconds, this is what delivered to us. So Giovanni Minuti, who is the PI of this observation, was completely surprised. He came to my office showing me this plot. And honestly, if XMM Newton didn't have 3 instruments on board, which collectively recorded the same signal, we would have thought that maybe the instrument was broken or something. Because really nothing like this had been observed from any extragalactic source. Now, the declination of the source is such that the visibility window of the XMM is quite small. So the source is visible typically during December and January, and then 6 months later during the summer. And just after the discovery, the visibility window was closing really fast, but Giovanni was able to obtain this director discretionary time observation lasting 1 full orbit. And this is what we observed. So this is a GIF image made of real data. So on the top right corner, you can see the epic PN, in this case, image of the source. And in the bottom, you can see the corresponding light curves. Light curve being to 200 seconds. And of course, this movie has been sped up quite a lot, but you can see the signal is there. So 4 very strong, very sharp bursts of X-ray emission were detected, spaced by about 9 hours in an impressively regular way, and lasting just about 1 hour each. So quasi-periodic eruption had been discovered, and they got this name under suggestion of Ari Laur, basically in order to distinguish them from the quasi-periodic oscillations, which are much more gentle modulation of X-ray flux observed many times typically in X-ray binaries, sometimes also in AGN. So QPEs had been discovered. This is a collection of the light curves, including the 4 that I've already shown you, and then also a Chandra observation, which was performed during the period when XMM Newton could not observe the source. And then again, in May 2019, when the XMM Newton visibility window was open again, another full orbit detected another series of QPEs from this galaxy. Now, the signal is absolutely striking, was again completely unexpected. And what was most striking was the extremely regularity of these bursts. But actually, they are not completely regular in amplitude and not even in recurrence time, in spacing time. In fact, if you look at the peak of the emission, you can see that there is an alternance of higher, lower, and higher and lower amplitude. And the same applies to the recurrence time, so the time separation between these bursts, which is shorter than longer, then shorter than longer. This can be observed also in these plots, which are related to this full orbit observations. So the amplitude is going up and down, and the same thing is doing the recurrence time. So this is really suggesting something possibly related to orbital motions around the central black hole. Spectrally, how do they look like? So first, the quiescent spectrum of the source. These on the left are the observed spectra in quiescence from 2010 in black until 2019 Chandra in green. And on the right, you can see the corresponding theoretical plot, which reproduce the model. And the most striking thing of this observation is the extreme softness of the spectra. So contrary to all the AGN that we know, most of the AGN that we know now, this source emits most of the photons below 2 kiloelectron volts. And the hard X-ray power law emission, which is somehow the signature typically of active galactic nuclei, is negligible. It's not absent, but it's very, very weak compared to what we usually observe. And if we fit the spectrum to a thermal black body component, assuming that it comes from accretion disk emission, a very small black hole mass for an active galactic nuclei is recovered of only about 400,000 solar masses. But how do the QP look like instead? So we performed phase result spectroscopy on the long January 2019 XMM Newton dataset. And on the left, you can see the average profile in 3 different energy bands, normalized to the quiescence level. So you can see that at low energies, the amplitude is much, much lower than at medium energies. And then at high energies, the amplitude is maximum. On the right panel, the same profiles were normalized to their peaks of emission in order to emphasize the differences in profile and in the peak position. And here you can see that at low energies, QPs are much broader, so they last much longer, and they also arrive later. So the peak is shifted at later times. And they are also much broader. I already said that they are also much more symmetric than the QPs at high energies. The phase results light curve was divided in several intervals, including pre-QPEs and then 2 rising phases, the peak, 2 decaying phases, and the post-QPEs. And then spectroscopy was performed on these spectral slices. And here you can see the results. So the QPEs, spectrally speaking, look like quite smooth oscillations between a softer quiescent level, here in red, and a much harder erupting state. So it goes up and comes down. And you can see the corresponding temperature and luminosity of the thermal component used to fit the spectrum. And again, there are smooth increases and decreases of temperature from about 50 electron volt in quiescence up to about twice that value during the peak of the QP. And correspondingly also the luminosity increases, reaching a peak of a few tens times to the 42 hertz per second. So we are speaking of very energetic phenomena occurring on very short time scales. Now, after these unexpected observations, we immediately started to look back in the archive, which is usually very rich of data, to see if we could identify the same phenomenon or similar phenomenon. We went looking at the archive with some sort of identity card of GSN 069. So galactic nucleus with a very small black hole mass, likely activated by a tidal disruption event, with an X-ray spectrum almost completely soft, so almost no photons above 2 kiloelectron volts, a high Eddington ratio typical of thermal emitting AGN, and also no broad optical emission lines in the spectrum. And the quest for QPEs in the archive led to 2 new sources. So the first one, J1302, was quite obvious because it was, I will show you in a minute, the properties that were already published in the literature were just strikingly similar to the one of GSN 069, and then J0249, which was much more hidden into the archival data and was discovered thanks to the clever application of an algorithm originally ideated for the exoplanet transit search by Johin Chakraborty, who was an undergrad student at Columbia and working with Erin Carr at MIT, who delivered the second strong candidate. So obvious things first, so J1302. This is a spiral galaxy which lies in the outskirts of the Coma cluster, and for this reason it had quite a few observations already in the archive, in the X-ray archive. It has a quite small black hole mass to be an AGN, and importantly, it has no broad optical emission line, and displays very peculiar X-ray variability already noticed in the Rosat era. So here you can see the Rosat spectrum in the top, which was completely, again, soft spectrum with the signal completely lost at higher energy, even though the effective area of the telescope also died at those energies. Very interestingly, the light curves of Rosat already displayed very interesting hints of peculiar variability, like this large jump in X-ray flux occurring on only a few tenths of minutes. Then in 2000, in the year 2000, X-ray Newton was observed in the Coma cluster with a pointed observation, and RxJ 1302 was just in the edge of the field of view, and this was observed by the EPIC instruments on board XMM. So this is a light curve of the source. On the top, the PN data, and on the bottom, the MOS data. The MOS cameras usually are open a few minutes before the PN, and this has been revealed to be quite determinant in our study of QPs. So it was obvious that there was a very peculiar, very narrow and strong flare in the PN data, but jointly with the MOS data, you can see that there was also the decaying phase of a previous flare. So this immediately called for asking a new rapid XMM Newton observation of the source, just to see if the phenomenon was still there, if that was the phenomenon or not. And this is what we observed. So on the left plot, you can see the archival data that I just shown you, while in the right plots, you can see the new observation taken 19 years later. On the top panel, you can see just the observed count rates as they are, in black for the large effective area EPIC PN camera, and then in red and green for the two MOS cameras. While in the bottom, you can see the count rate divided by the quiescent level. So you get an idea of the relative amplitudes of these signals. So QPEs were observed in RxJ again. This means that in this source, the QPEs have been present at least for about 20 years. They are very short, so they last more or less a half of the duration of the QPEs of GSM 069. And also the time separation between them is not that clear. While they also follow a long, short time separation pattern, the separation that we measured between 2000 and 2019 were all different. This is a collection of light curves of the source taken in different energy bands, from low energy at the top up to the highest energy at the bottom. And highlighted in blue are the peaks at the highest energy probed. So it can be seen by eye already that also in J1302, the QPEs at low energies peak later. So the QPEs somehow arrive first at higher energy, they peak first at higher energy, and then at lower energies. And they also are very, very short at higher energy, reaching a duration of just about 15 minutes at the highest energy probe. And then above 2 kV, again, the signal dies off. There is also, again, the difference in times of arrival of the peaks at different energy, which is a significant fraction of the time separation between consecutive QPEs. So this might be telling us something important about the physics behind this phenomenon. Spectrally speaking, J1302 also looked pretty much like GSM 069. So on the left, you can see the 2000 data. In the middle plot, the 2019 data, and then in the right panel, the corresponding theoretical models for both epochs. And in both epochs, the quiescent spectrum is a thermal component, almost purely thermal component with a very low power law emission, with a temperature of about 50 electron volt. And then during the flare, the temperature rise up to about 100, 120 electron volt. The temperature of the flaring state is higher in 2019 than in 2000. And also the power law level in quiescence is slightly higher in 2019 than in 2000, even though the background at these energies starts to become quite an issue for the observations. Then J0249. This is, again, this is a source which was found in the archive thanks to the application of the CATS algorithm. This source had quite a similar story to GSN 069 in the sense that it was not detected by Rosat in the 90s, and then it was discovered in the X-rays by XMM Newton during this slewing process from a target to another. And then it was studied again and monitored by Swift to see if the flux evolution was consistent or not with a TDE. So this is the X-ray light curve of this source from 2004 up to last year. And there is a decay in X-ray flux, again, consistent with a tidal disruption event. The XMM Newton spectrum taken in 2006 shown these 1.5 QPE-like flares. So this feature was the feature that the algorithm was able to identify and pick up in the archive among the myriads of observations. And this flare is also followed by the rapid rise of flux at the very end of the observation. So we don't call this object a TDE source for the moment because only 1.5 flares were identified. Of course, after this discovery, a new XMM Newton observation was asked for and was performed in August 2021. And this is what we observed. So there are no QPEs in the light curves anymore, but the source flux is still very flat. So the flux level is very flat and is reminiscent actually of the observation of GSN 069 when it didn't display QPEs. So for these reasons, we call this source a QPE candidate, but we are really confident that we are observing a similar phenomenon to the one observed in GSN 069 and in J1302. Also because of the spectral properties of the source. On the left, you can see the spectra taken in quiescence in blue and during the flare in red in 2006. So the spectrum is very soft, dominated by a thermal component, which is slightly hotter than what is observed in the other two QPE sources. But again, it's colder than the temperature measured during the flare, which is about twice hotter. Then in 2021, sorry, the spectra of the source looked like this. So while it's still quite dominated by soft X-ray photons, there is a non-negligible hard X-ray component now. So something is happening to these sources during these years. So in the meanwhile, while we were scrapping the archive, the German-Russian observatory spectrography was launched with the Rosita on board. And the Rosita delivered quite unexpected, again, results. So two sources were discovered during the first 9 months of operation of the survey of the X-ray sky, ERO-QPE1 and ERO-QPE2, ERO-1 and ERO-2 for short. So in this slide, you can see in the top panels, the eRosita light curves. So eRosita scans the sky and makes a revolution about around the Earth every about 8 hours. So this is the binning of these light curves. And in both cases, there are huge increases in soft X-ray flux observed. Sometimes yes, sometimes not, and then again. And so immediately after observing these results, Riccardo Arcodia asked for XMM Newton and nicer follow-up of this of these QPE candidates, and this is what he got. So in the top panel, you can see the nicer monitoring of ERO-1. It's evident that this source also displays quasi-periodic eruption of X-rays, and the time separation between them are quite large. So this is almost 1 day of separation between eruptions. And they are also very energetic, so even much more energetic than the QPEs of GSM. And then ERO-2, on the contrary, had a very short separation between its QPEs. So in this case, the separation is only of the order of 2.5 hours, so even shorter than what was observed in GSM. And also the duration is very, very short. So it's comparable to the duration of J1302, more or less half an hour for each QP. Spectrally speaking, these sources also look pretty much like the other ones that I've shown you, meaning that the spectra in quiescence are very thermal-like. So in the top panel, you can see the Rosita spectra, which are taken all together. And then in the bottom panels, you can see the XMM Newton spectra of the two sources. And again, the super soft spectrum observed in quiescence becomes much harder during the QPs. The spectral evolution following time, the time evolving spectral evolution can be also observed in these plots. So on the left, ERO1, and on the right, ERO2. And the evolution again is smooth. So during the QPs, the spectral parameters do not show any abrupt change, but they just smoothly follow the flux evolution. It is worth noting that the temperature of the QPs of ERO1 are much higher than the other, but especially the timescales involved are much, much larger than the other QP sources. In the case of ERO2, while the timescales are really, really short, both in terms of time separation and of duration of the QPs, the temperature is quite similar to what is observed in the other sources. Surprises from the ground. So while at the beginning of the discovery of the Rosita sources, the galaxies looked like completely quiescent galaxies, a careful examination of optical spectra taken from ground revealed that there are narrow emission lines in all the QP sources. Narrow emission lines whose fluxes are compatible with the presence of an ionizing source of photons different from purely stellar light emission. Also, the authors of this is a paper led by Thomas Wevers. It just appeared in the literature. They measured the black hole mass, they estimate the black hole mass of the sources using the velocity dispersion, and they confirm that the black hole masses of these sources are very small compared to the active galactic nuclei population. So we are speaking of 10 to the 5, at most a few times 10 to the 6 solar masses. Also, it is worth noting that this work demonstrates that there is a large fraction, incredibly large fraction of very rare galaxies among the QPE hosting galaxies, meaning at least 2 of them, J1302 and ERO1, are very rare post-starburst galaxies with a recent starburst stopped. So this is a collection of light curves of the 4 confirmed QP sources observed by XMM Newton, and each beam here is 1 minute. So you can appreciate the differences in the phenomenology of these sources, especially ERO-QP1 is really different from the others. You would not guess that this is a QP source just looking at this light curve probably. So to summarize the properties of these QP hosting sources, they are extremely soft sources which have almost no photons above 2 keV. And QPs are very likely associated to tidal disruptions of stars or compact objects or something onto massive black holes of not too large mass. The duration and time separation of these QPs is quite various, so it varies quite a lot among different sources. The luminosity carried is significantly high, significantly large, so of the order of 10 to the 42, 10 to the 43 ergs per second in each QP. And QPs look like spectral hardening and like with an increase of temperature compared to quiescence of a factor of about 2. So what are QPs? We still don't know. This is the short answer. And there are many words already trying to interpret this phenomenon, and they don't even know all the observational details yet. So 2 main broad physical scenarios to interpret these signals are accretion flow instabilities So for example, the appearance of this burst is similar to the heartbeat states observed in black hole binaries sometimes, which are reasonably explainable with radiation pressure instability. But this cannot be the case for our QPE sources because the timescales are completely off. So the QPEs are much more rapid than what you would expect for radiation pressure instability of the inner accretion disk around a massive black hole. And or the luminosities are too large. So if we are speaking about accretion flow instabilities, we must think of either radiation pressure instability in a different geometry, different physical configuration, for example, optically thick and geometrically thick matter, or to some sort of dynamical instability, for example, in an inner disk tearing, or even magnetic instabilities. To the first or the other big physical scenario to interpret the QPEs is, of course, orbital motions, because given the oscillating amplitude up and down and the time separations, which goes also up and down, it's quite natural to think to one or more objects orbiting the central black hole and doing things. So in orbital phenomena, there are also two main broad physical scenarios. One is gravitational lensing. So in this case, you have two massive black holes of more or less the same mass orbiting each other, each one which is with its very small accretion disk. And then if the orbital inclination is close to edge on, you can see twice per orbit gravitational self-lensing of these accretion disks. Or you can have purely, let's say, orbital phenomena, where you can have either stars doing a mass transfer through Roche lobe overflow, or also impacts, so direct impacts of compact objects onto either disk or torus or the accretion flow around the black hole. Now, the first class of models, the accretion flow instabilities to the first order, they have a big problem together with the gravitational lensing scenarios, which are the shape of the flares predicted. So to the first order, the gravitational lensing predicts a very symmetric flare with the proportion between the duration and the amplitude completely off to what is observed in QPEs, which are much more intense than what is predicted. But recent studies of gravitational lensing suggest that there might be more complicated physical phenomena going on, which can deform, we can distort quite a lot the predicted profiles of the flares. So perhaps this channel is still not closed yet. For the radiation instability or dynamical instabilities, there is the same kind of problem, meaning to the first order, the predicted shape of the flare is completely off, even more than in the gravitational lensing case, because radiation pressure instabilities in general predict a much slower rise of the flux and then a very sharp decay. And this is contrary to what is observed in QPEs, where if they are not symmetric, they usually display a much riser fast and then a slower decay. But again, if one considers the effects of very strong magnetic fields, for example, of a completely different scenario, which would be magnetic instabilities, the problems related to the shape of the flare could disappear. So these scenarios are disfavored at the moment, but we cannot really say that they are ruled out yet. Orbital phenomena are very promising, and they have not been falsified yet, even though we don't even have that many predictions yet, to be honest. But anyway, they are very interesting, especially because they can represent extreme mass ratio spirals. So when you have a very large object, like a massive black hole in our case, and a much smaller mass object orbiting it, eventually the two will merge due to the release of gravitational waves. And they might also emit some electromagnetic signature. So this electromagnetic signature might be what we are observing as QPEs. And there have been many, I think more than 10 now, different scenarios in this orbital scenarios again. So the first one was King already in 2020. He proposed like the remnant of it was the partial destruction of a red giant in GSN 069, and then the compact core of a white dwarf in a highly eccentric orbit, producing the QPEs at every passage close to the black hole. And then there have been variations on this model, like considering a star in a less eccentric orbit, or considering even two stars in coplanar orbits and doing reciprocal mass transfer when they approach the central black hole. In the case of impacts, two main accretion flows scenarios have been explored. So either a thick torus around the disk, or which is perturbed by compact objects going around, or stars plunging in the accretion disk around the massive black hole. And I will spend 3 minutes focusing on this very last scenario by Xian and collaborators, because it has many promising openings for the future if confirmed. So in this scenario, it is assumed again that there are one central large black hole and then one compact object, a star in this case, orbiting it, and then impacting the accretion disk while it goes around. Then, by studying the distribution of the time of arrivals, so the peak position of the QPEs, in principle, one can reconstruct the space-time metric around the massive black hole. So you would expect different trajectories of both the objects and the photons emitted in the case of a rotating black hole or not. And this means, vice versa, that measuring with a high precision the time of arrival of QPEs, you could constrain the black hole spin. And this could be amazing, because we could have a method which is completely independent from any spectral modeling and assumptions. So very promising. Also, the quite exciting development which can happen in the future is the detection from space of these phenomena in gravitational waves. So studies here are still controversial, but there are some articles which show promising results in terms of the expected strain in gravitational waves and the sensitivity curves of future space-based gravitational waves observatories, such as the European LISA or the Chinese Tianqin. So the science touched by the QPEs is very broad. They are probably telling us something very important about the connection between active galactic nuclei and tidal disruption events. This is linked, of course, to the evolution of galaxies by definition, and the evolution of low mass AGN. In the future, they could even reveal to be a way to measure the black hole spin, and they could be revealed in gravitational waves from space. But all in all, it is very difficult to imagine which other surprises we would get. Why? Because I didn't show you all the things that we observed so far. So there are many more complications in the data that we got. I will show you a few of them, a few puzzling results. So the QPEs in GSN 069, where are they? We don't know. So in the top, you can see the light curves that I showed you already before of the QPEs of GSN 069 until May 2019. Then 6 months later, in January 2020, the QPEs were still there, but completely, I mean, looking in a completely different way. So they were much weaker and much less regular. And then 6 months later, there is no evidence of any QPE on these timescales probed, which are 1 XM orbit. So more or less 2 days. So we don't know. Perhaps QPEs in GSN 069 are a recurrent phenomenon. Perhaps they are gone forever, or perhaps they are happening on timescales longer than 1 XM orbit. We don't know. RxJ 1302. Of course, as well, after the puzzling result that we got in 2019, we asked for new X-ray observations, and we got a full XM orbit in August 2020. And this is the result that we got. So the light curve is here in the right panel. This was a very puzzling light curve. So for the first time, we detected 2 very small amplitude QPEs. And in general, there is no easily discernible pattern of separation between the QPEs, meaning every time that we observe them, they seem to be separated by a different amount of time. So this is quite difficult to reconcile with a simple orbital scenario, with a simple scenario of any sort. And if you look at the second half of the observation of the last part, it almost looks like the QPEs are arriving in pairs. So like a first pair, second pair, and third pair of QPEs. And when we did the spectral analysis on this data, we observed that there is a hint of alternating duration, so long, short, long, short, long, short duration, and temperature, meaning that the longest QPEs seems to be the coldest, and then the short QPEs are hotter. But again, this doesn't last the whole observation, but just the very end. So big puzzle, but stay tuned for something appearing in the literature soon. GSM 069 in quiescence, another big puzzle. It looks like that during the Chandra observation, which was performed just 1 month after the long X-Newton orbit, the temperature observed in quiescence was much larger than what you would expect from the luminosity. So while the quiescent spectrum really follows very, very well constant area black body evolution in the X-Newton point, it does not during the Chandra one. We don't know why yet. Radio properties of the QPEs. So I didn't mention this during this webinar so far, but we don't observe any kind of significant variability in the UV contemporary to the X-rays. So this phenomenon seems to be really limited to the highest energies. We went, on the contrary, to observe at the lowest energy, so in the radio band, in February 2019, contemporary to the Chandra exposure of GSM 069, 3 radio observatories were observing simultaneously, but unfortunately 2 of them didn't cover the eruptions exactly. Meerkat was covering the first QPE observed by Chandra and did not observe any significant variation in radio flux. But we cannot say if the radio flux was varying before or after the QPE, for example. So all in all, a quite inconclusive result. Much more promising, but still quite inconclusive result is for the radio emission of J1302. So in this case, we observed the source with X-Newton for 1 orbit, contemporary with 9 hours of exposure with the very large array. And in the top left panel here, you can see in red the X-ray light curve, which is a portion of the light curve that I showed you before, and in blue, the simultaneous radio exposure. And each beam is 1 minute, each time beam. And on the bottom plot, you can see a zoom close to this QP number 6, where we observed an increase and decrease of X-ray flux, and then just a few minutes later, more or less 4 sigma significance radio flare, which is lasting only 4 minutes. So extremely short duration. Now, we don't observe a similar flare after the other weak X-ray flare, but this flare in X-rays is also much weaker than the previous one. And unfortunately, due to orbital constraints, basically because of also the high, in this case, declination of the source, the radio observation had to be split in 2 segments. And by bad luck, the gap in the data was exactly coincident with the large X-ray QPE. So we don't know if after this large QPE there was any correspondingly variable radio emission or not. But luckily we are trying to perform this experiment again. So either this summer or this for coming winter, we should have the X-ray and radio observation performed again with twice the amount of time coverage. So let's see if we are more or less lucky. Then ERO-QPE1, which is an amazing source and very different from the other in terms of time scales involved. So the very long time scale allowed to perform a detailed spectral analysis, and this is a work led by Riccardo Arcodia, which is going to appear very soon in the archive. So what was observed is that during the QPE bursts, there are actually, the QPE bursts are formed by multiple bursts. So in this case, the data require 5 different bursts, of which some of them are overlapping, some are not, some have a much lower intensity than the others. And very interestingly, they vary in a color-dependent way, in an energy-dependent way. So in the bottom right, you can see the hardness ratio for 3 bursts. So the first 2, the first in red, the second in green, and the last big flare in blue. And in all the cases, it can be seen that given a count rate, the rise during the QPE is much harder than the decay. So the decay of the QPE is much softer than the rise. So the situation is complex, it's more complicated than we expected, also because this occurrence of multiple bursts is not always constant, because there is another observation of the same source performed with the same instrument, which is XMM, where the light curve is fitted perfectly well by a single burst with the same shape of the others. So again, there is much more complexity than we were expecting. And this, of course, calls for a huge space of discoveries, space of discoveries for future observatories. So, Athena. Athena is the telescope of the future, is our telescope of the future, so it will observe QPEs. This is my summary slide of the Athena results, so it will come back at the end, at the very end of the seminar. So what do we want to study QPEs in the future? We want the largest effective area possible, basically. This is the dream maybe of most of X-ray astronomers, but this will be very important for the QPE studies. So with the large effective area that will be offered by the WFI and also by Xiphon, we will be able to perform time result instead of merging all the QPEs all together. We will be able to perform time result spectral fitting also in much less brighter, much dimmer sources. Very importantly, we will be able to study the quiescent flux in detail, which is something which is at the moment very difficult to study, because the 2 Rosetta sources has a very low quiescent level, which is completely consistent with the background only. And the XMM Newton background is very high, above 2 kiloelectron volt for these very steep spectrum sources. So we really don't know if there is a power law component participating to the QPE phenomenon or not so far. And Athena will answer this question for sure. Now we observe QPEs recurring on a minimum of 10 kiloseconds, but up to several hours. So in order to detect them, we would need a minimum exposure time of about 20 kiloseconds. In the luckiest case, when the QPE are separated by a small amount of time. And in order to study cycles of QPEs, obviously we would need a much longer exposure time. So in order to follow the evolution of a cycle, we would need at least 100 kilosecond observation. And in terms of timing capabilities, we will be super happy with what we have, because we don't need an extremely good timing resolution. A time resolution of a few seconds is perfectly fine to constrain the peak of arrivals of the QPEs. And so if the orbital scenario is correct, to constrain the black hole spin. Specifically, the wild field imager will be fundamental to enlarge the numbers of sources known, because we know a very small number of sources with QPEs, and the most efficient way to discover them has been through slewing from a target to another. So we might expect that in survey mode, the WFI will be observed a very large field of view for a long amount of time. We can expect to discover new QPE sources. And studies of QPEs in general can be pushed to higher redshift thanks to the larger effective area and the good spectral angular resolution of the instrument, not too large redshift, because these sources are very soft. So we will lose all the signal at a redshift more or less above 2, but there is a lot of cosmos between redshift 0.1, where are we now, 0.05, better where we are now, and redshift 2. So huge space for discoveries. The integral field units also has the potential to be fundamental in helping us understanding what is the physical mechanism behind QPEs. Why? Because gas is predicted to exist along our line of sight. Because whatever is the origin of the QPEs, they are doing something to this gas, which is warming up. So we expect to be able, with the XIFU, to detect this gas and possibly also to detect the dynamical variations of this gas. Something important to mention is that the column density that we expect are likely very low compared to what we are used to as X-ray astronomers. So maybe just of the order of 10 to the 20 per centimeter square, maybe no more. And the gas could also be very highly ionized, so imprinting very few spectral transitions in the spectra. So the high spectral resolution of the XIFU will be fundamental to give us more understanding. Finally, LISA, the multi-messenger perspective on QPEs. This is, of course, very speculative because we don't even know if the physical scenario is correct to interpret this phenomenon, but maybe it is. And if it is, it could be that actually we anticipated LISA at X-ray, so we are observing something that LISA is expected to routinely observe in the 2030s. And then if so, maybe, who knows, but in the future, ESA will have to change or add a subtitle to the Athena and LISA synergy. We might maybe also be able to observe massive black hole, not supermassive, but massive, growing in real time, like bit by bit or byte by byte also, if they're eating stars. So this is, again, this is the outline of what Athena can do for us in the next decade. But my main message is really expect the unexpected, because this has been the main learning from this story so far. So I will stop here and I will take any question that you might have.
Thank you very much, Margherita. It was extremely nice and very clear, and very nice results indeed. Yeah, I already see a couple of hands raising. Matteo, I think you can speak because you're a panelist. Go ahead.
Yes, thank you, Nanda. Above all, thank you, Margherita. Very exciting results. Looking forward to what you alluded to, and we're not allowed to mention, I guess, why. I have a question on the interpretation of QPE related to one of the evidence that you were showing, and namely that it seems that the QPE happens first in the harder energy band, and then later in the softer energy band with a sort of broader shape, which may suggest some sort of reverberation phenomena where maybe something happens in the hard and then it's propagated in the softer part of the disk, maybe following the light crossing time between the position of the hard event and the outer region of the disk where the soft emission is created. Is this interpretation meaningful, and if so, doesn't it rule out interpretation based on purely orbital phenomena?
Thank you, Matteo. That's a very good question and a very good point. So the answer to the final question is yes, it would rule out the purely orbital motion if we could demonstrate that the signal starts in the hard band and then propagates into the softer band. But there is a observational complication. So in this case, here you're observing GSM 069, which was you can see here that the higher energy peak arrives earlier, and then the medium energy and the lower energy arrived later. But the signal to noise was not large enough to assess who starts first. On the contrary, in ACO QPE1, where the timescales are incredibly larger and the statistics is much larger in terms of X-ray photons, it was possible to demonstrate in this case, and I'm sorry, I don't have an extra slide for this result, but you will see it in the archive very soon because this paper is really almost accepted. So in this work, it's demonstrated that the bursts also start before at lower energies. So they start, so if you come back to GSN 069, you cannot see it here from this plot because you don't have the way to see it. But if you believe me, this red curve also begins before the rise in flux of the blue one in ACO QP1, which is the only source where we could try to separate, well, where Ricardo could try to separate the exact starting point of the rise in the flux. So it would look that judging from the ACO QP1 observations, it could not be this kind of reverberation. Then I don't know if ACO QP1 behaves differently from the other sources or not, because we cannot do the same kind of analysis on these other sources because of lack of statistics.
Okay. Thank you, Margherita.
Sure. I don't hear you.
Hello.
Yes.
Yes, wonderful talk. Thank you very much. I think these are absolutely fascinating. You mentioned that one scenario was some kind of orbital phenomena. I think that sounds like really interesting and cool to think of. But a few of the sources had some significant irregularity in eruption times, and not just like the one with like where we're potentially coming in pairs, but even some of the other ones, they'd be like a matter of hours. Yeah, like that, like there in the ACO QP1, there's like a matter of hours between each eruption. Could something as regular as a orbital phenomena still have these sort of regularities?
This is also a good question. My short, easy answer would be that the universe is demonstrating to have much more imagination than we do have somehow. So I would not say this is not possible. There might be, for example, like there was a very recent study about the eccentric mergers of massive black holes in AGN disks, where it was demonstrated that the AGN disk can enhance the probability to have eccentric mergers. This implies that the AGN disk might be full of binary or triple smaller black holes. So for example, if this is not a simple single object orbital motion, but maybe two objects in complicated geometries, I don't know.
I was also wondering if like the motion of it would cause, I mean, it would obviously cause irregularities in the accretion disk. So you know that might matter as well.
One thing I should mention is that in the double coplanar orbiting model, when they what in the sketch in this multiple Roche lobe overflow model, when the authors consider the presence also of the accretion disk, and they can see variable amplitude of the flares and variable recurrence times between them. So basically, the presence of a disk adds irregularities to the expected light curves. So this might be another possibility. Is that both mechanisms are somehow happening, like some kind of orbital event or motion can trigger instabilities on the accretion flow that can then propagate in. But honestly, we really don't know. Like the data have so many details which are not really compatible with the simple scenarios of any sort, which are, I'm completely puzzled in general. I tried to keep it simple for this talk, but it's...
It really is fascinating. Thank you very much.
No, thank you. And sorry if I cannot properly answer, but I don't have the answer.
Thank you. Next question is from Daniel Wang. Maybe he can, I will allow him to speak. Can you speak? Yes? But you have to unmute.
Can you hear me?
Yes.
Yes.
Okay. So my question is, how could you compare what you see in other sources with flares observed from Sagittarius A star? What kind of insight one might learn from such a comparison?
Hi, thank you for this question, because this is something about which, I mean, my mind is thinking about this quite a lot lately, like in the last few days, few weeks. And so observationally, the comparison is very interesting, meaning that the shape predicted from magnetic recognition simple models for Sagittarius A star, the shape of the predicted flare is very similar to what we observe, for example, in ACO QP1 or XJ 1302, meaning a very fast rise and then a much slower decay. So the shape is correct. And what is the main issue that I have with this model, personally, is that they are all computed for the accretion flow, which is expected around Sagittarius A star, which is a very low luminosity nucleus. So the accretion flow is usually modeled with an ADAF, or with a relatively inefficient accretion flow, and usually also the configuration is assumed to be a magnetically restive disk. And then in that case, there are, if the flow is a magnetically restive disk, there are nice similarities between what is predicted for Sagittarius A star and what is observed in terms of shape of the flares. But then I have the issue of the physics behind this, because I would like to see some simulation, theoretical expectation, not simulation, but some theoretical predictions for what is expected in terms of magnetic recognition, but in a optically thick, possibly, accretion flow, which is something extremely difficult to study. But it's something, it might be the direction where the QPEs are driving us. I still don't know. So it's a work in progress, I would say. But it's a comparison which is very inspiring. Also, the black hole mass is very similar between Sagittarius A star and RxJ 1302, but then they behave so differently in X-rays, which is some big physical difference must be also there.
Thank you. Can I ask a follow-up question quickly?
Yes, of course.
Yes. So how about time scale? You just comment on the similarity of the black hole masses, and then time scale seems to be pretty compatible. So in terms of intervals between the flares and also the duration of flares. So this might be some insight one potentially can learn from such comparison, right?
Yes, no, you are completely correct. In fact, this was why I was commenting that the black hole masses are similar in J1302 and Sagittarius A star, because there are works with predictions of the timing of the flares of Sagittarius A star, and the timings, the time scales predicted are good, are okay for us. So, but again, the predictions made on Sagittarius A star are made assuming an accretion flow, which is probably not the accretion flow that is present in these sources, but very promising comparison. And indeed, I'm thinking about it quite a lot.
Thank you.
Thank you.
Great. We have actually yet another question, which is Robbie Webby. Do you want me to allow you to talk? Yes. Oh, I'm not sure I hear you. Yes. Can you
yes.
talk? Yes, great.
Perfect. I was just sort of thinking about the sort of quite wide range of amplitudes of flares that have been seen, and sort of combinations of recurrence times and eruption widths. Obviously, if you have sort of flares which are closer together but have a longer duration time, like the ones maybe which are seen in the nicer observation of ERO 1. I was wondering, at what point would you start to define something as being a quasi-periodic oscillation as opposed to an eruption?
This is an excellent question, and this is something that we didn't think about it yet. But we will need to, I mean, the only person who probably thought about this is Johin Chakraborty, who is the lead author of this work. So he had to apply some kind of filter to the signal to noise of the possible QPE flare in order not to pick up just much lower amplitude oscillations, but we don't have any formal yet threshold used to define the thing. If you look at this flare and you smooth it just maybe by a factor of 3, you would have something that looks like a QPO, indeed, not like a QPE. So in this case, with low amplitude, we are close to the, where the distinction between these two phenomena maybe fades. We don't know. I should mention that there are hints of QPOs during the quiescent evolution of GSN 069. And also there is the claim of a QPO in one of the segments of the observation of RxJ 1302, also during the quiescence. But then with the new data of RxJ 1302, with a much longer timeline, we were not able to confirm the presence of such QPO. So there might be physical links between the two phenomena, not only the similarity of their acronyms, perhaps they have more links, but we don't know yet. But at some point, especially if the number of these sources increases, we will definitely need to think about this question. So where to put a threshold in terms of duration or relative intensity to separate QPs from QPOs. So thank you very much.
Thank you.
I think we have one more question in the chat. I don't know if Anatoly wants to ask the question himself. Maybe yes. Can you speak? Anatoly, you can speak. You just have to unmute though. No, if you want, I can read the question. So his question was, should we expect the appearance of a relativistic iron K-alpha line in the X-ray spectrum if we accept the picture of a change in the type of accretion due to instability?
Okay, in principle, if I didn't know anything about the spectra of these sources, I would say yes, we do. But then looking at the spectra, we don't have any photon above 2 keV basically, so I don't see which photons could produce those lines to begin with. So at the moment, I mean, unless, but again, we have been surprised continuously, so I will shut up. But at the moment, it seems like the iron K complex is not part of the story. But now that I said that, maybe in the next
Okay, thank you very much. I think we don't have, yes, one more. Massimo, you can talk.
Yes, can you hear me? Yes. Thank you very much, Margherita, for this very nice webinar and amazing results. It's not the first time I see and hear these results, but every time I'm amazed on the how interesting and puzzling they are indeed. I have a question, a quick one on you may have explained or explained already, but can you say again what kind of spectral information you have in the quiescent state? I mean, in between the QPEs, in between the flares, what type of spectral information you can obtain?
Yes. Again, I'm sorry because I don't have the. I would like to show you some extra slide, but I didn't prepare them. So let me see where I have the spectra.
Also to follow up on the question on the similarities with Sagittarius A star, because if you could have optically thin emission in quiescence dominating the quiescent state, you would you would expect some kind of Bremsstrahlung-like spectrum in quiescence.
Right. Yes. No, the problem is that the spectra, they really look very soft, so it's difficult to reproduce them with even a thermal Bremsstrahlung is probably broad, too broad, but I'm not sure. The thing is, the information that we can get is there are these hints of oscillation. So the quiescence might go slightly up and down, following kind of QPO lifestyle oscillation, but this is statistically not proven yet. Then there are hints of absorption, warm absorption, low column density, warm absorption in GSN 069 when there are no QPEs. But there is no absorption when there are QPEs, for example. RxJ 1302, the same, it has some hints of low column density absorption during some of the QPEs, but not in all of them. So there is some information in quiescence, both from the timing point of view and from the spectral point of view, which is probably there, but we are not able yet to extract this information from the noise somehow. And then the like broadband evolution is, I mean, it's difficult to say, because in this case, in GSN 069, the quiescence, as I show you in the puzzles, look like perfect black body, but not in the Chandra observation. And then the power law component is also very puzzling, because it really is in a region where the two.
But sorry, Margherita, excuse me, but the black body emission is only for the flares, or it's
no. It's the quiescent spectrum is a black body basically.
Oh, sorry. Okay, I missed that point. Okay, so it's also a black body.
So here you can see in red you have the quiescence basically. So it's a pure black body. It doesn't even have a strong power law emission.
Okay.
It's very difficult to compare it with Sagittarius A star directly, because it really looks like a thermal spectrum. It doesn't look like non-thermal emission.
Okay, so okay, thanks. I missed that point. Thanks.
The complication that we have is that where these two components merge, so that the thermal component and the possible power law component is also where absorption might appear, or warm absorption might appear. So it's very difficult to say if there is absorption, if there is not, if there is a power law component of its unmodeled absorption. So okay, we will need many more photons. So Athena.
Okay.
We'll wait.
Yes. Thank you.
Thank you.
Thank you very much. Maybe one last question. Then, from the black body, can't you derive a surface, an idea on the dimension of the emitting region?
Yes, you might. And
how big it is compared to the typical dimensions of the disk?
Or just whatever
very small.
radial region with to constraint, it results to be very, very small. So a few tens of gravitational radii.
Yeah.
I could give you a number, maybe 30 gravitational radii. Very small, very compact emission region.
Okay, thank you very much. I see there are no questions. We went a bit out of time, but this was so interesting that it was definitely worth. Thanks a lot. Thanks a lot to the attendees and the panelists and everybody, especially to Margherita, of course, for giving this wonderful talk. And we'll definitely meet in the next webinars, I hope, in April, which will be Melanie Habuzit, I think. But the community office will definitely release the announcement very soon. So thanks a lot. And thanks, Margherita.
Thank you.
Have a nice day.
Thanks. Bye.